Hi students, this is my video number 28. Now we look at the flux in the more general surface. Flux in more general surface. So for any surface M, for any surface S, see, where a point P on S. So we have, let's say this is our surface S, and we have our point here. Okay, so where it can be written as we have R UV as X UV I plus Y UVJ plus Z UV K. Yeah. So where R is a position vector of those points, so of course you can consider this somewhere, let's say from origin. So this is your R. So it can be represented as a two parameters U and V. Okay, so from here you can, if you differentiate with respect to one of them, that will give you the tangent to that. All right, so if you differentiate, let's say with respect to U, that will give you tangent to it. So let's say this is your U, and if you differentiate respect to V, maybe somewhere you have RV, like that, still tangent to the surface at that particular point. And if you cross product with these two, that will give you a normal to it. Yeah, this gives you normal to it. So with that idea, if we consider L as del R del U, and we consider M as del R del V, okay, and then normal is given as unit normal is given as L, this is vector L cross M divided by magnitude of L cross M. So therefore the surface integral, we have S F dot N ds, let's say this is equal to, we have our N is given as that, and N ds ds as we need to change to du dv. So we have, this is, say, S F dot our N is L cross M over magnitude of L cross M, right? And then for ds we have L cross M du dv. So of course you can cancel out this, then what left is that SF dot L cross M du dv. Now let's see example for this. Now consider one example. Let's say we have a vector field given as F as XYZ x, y, z, and S is a sphere with radius a. So in this case, we have the radius of a sphere rho. This is a. Oh, it's not focused. Okay. So we want to find flux. Find flux. So what we mean here is that we have a surface. We have a surface, a sphere. Let's say that a sphere, and we have a vector field. We have vector field, whatever direction is, right? So let's say that. So we want to see whether how much flux that cross, or how much vector field cross the surface of those sphere, right? So we know that for a sphere with so this is our rho, this is right, okay, so xy, so we have those, that, okay, so we have xy, so this given as theta, this given as phi, that's rho. So for this, the representation of sphere coordinate that we have explained some times ago, that we can write x for each point on the surface. You can write x as the radius of the sphere A sine of phi cos theta, and y is A sine phi sine theta, and z is A cos phi, where phi 0 to pi and theta 0 to pi. Maybe you can think of why we have these limits. Why, for example, phi we not consider 0 to 2 pi. So try to think of those things. And we want to find the flux, yeah, for those vector field across the sphere. So we know that the flux is given as SF dot n ds, right? And this is we have shown in the previous just now. We has F dot L cross m, d, in this case d phi d theta. Okay, so we need to write a point on those surface in terms of vector notation. So our r, position vector at any point of on the sphere, and these are depend on phi and theta, because r is fixed, or rho is fixed, which is a. So in this case we have, you know that this is x is given by this, y is given by that, and z is given by that. So we have this vector. So we have a sine phi cos theta, and y a sine phi sine theta, and z is a cos phi. That's our position vector on the for a point on the surface sphere. Now, having obtained r, we need to find what is L, which is del r del phi. Yeah, we differentiate that with respect to phi. So what we have, that give you, this is a, sorry. So we have a cos phi cos theta. This one we have differentiate is phi, so a cos phi sine theta, and this one we have minus a sine phi. Alright, and for m, this is vector, which is del r del theta. That gives us differentiate that with respect to theta, so we have minus a sine phi sine theta. That one is a sine phi cos theta, and that gives you 0. Okay, and then you need to find what is n, unit normal, because here we have unit normal. So our n is given as L cross m over L cross m. So if you look at our formula here, so we just need L cross m. So find this, because we already have what L is, we already have what m is. Okay, then you just need to find what is L cross m. So for this we have L cross m is L cross m. Again, if you find the determinant, we need this I, j, and k. Don't forget this I, j, k. Many students left this out, and what left is determinant of matrix 2 by 3, which is basically you cannot find it, right? Okay, so for L cross m, we have L is here. We have L, this is our L, so there's a first component, second and third, and as well as that. So we have, let me write those things, A cos phi cos theta. Second component is A cos phi sin theta. And third is we have minus A sin phi. Whereas for M, we have first component is minus A sin phi sin theta. The second is A sin phi cos theta, and this one is 0. Then you can find this. So what we have here is that okay, for I, so we have 0 minus those things. So we have a squared sine squared phi cos theta, right? For j, we have that one a squared sine squared phi sin theta minus, you got 0 there. And for k, we have a squared cos phi sin phi and cos squared theta minus, we have so minus you got plus, you got a squared cos phi sin phi and sin squared theta. Of course, from there you can simplify this. Right, for this third terms here, we have, you can factor out a squared, you can factor out cos squared sin squared, and then you have cos squared plus sin squared, that gives you 1. Then the result is a squared cos phi sin phi. And then here from there you can have sine phi. Here you have sine phi. Here you have sine phi. You can take out all those a squared sine phi from all those terms. So what left is, here in this case, you have a squared. You can factor out a squared, and then you can factor out sine phi. So what left is that, in this case, you have sine phi cos theta, sine phi cos theta. Here we have sine phi sin theta, and here you have cos phi. That's all. Alright, and then you can just plug into your formula here. That's our formula. So therefore we have so integrate over SF dot L cross M d phi d theta. Okay, that give you we integrate for phi 0 to for phi 0 to pi, for theta 0 to 2 pi. Then inside there we have your f. Our f is given here. We have x, y, and z, and x, y, and z is this in spherical coordinates, right? So just substitute everything in there. So what we have, our x is our f is a sine phi cos theta, y is a sine phi sin theta, and z is a cos phi. Dot with that dot. Yeah, do not confuse dot product and cross product, two different things. Cross product give you scalar, and dot product give you scalar, and cross product give you vector. And also the way we perform those dot and cross product are different, so do not interchange those things. Then for R L cross M, which is you have here, so we have dot a squared sine phi, and we have sine phi cos theta, sine phi sin theta, and cos phi. So we integrate theta first, d theta d phi. Okay, so at this point, I think you should have no problem to evaluate those integrals. First thing, you need to perform the scalar product of those. That phi from 0 to pi, theta from 0 to 2 pi. Then you have here a squared sine theta. Here you cannot factor out, so just take out a. So we have a cube sine phi. Okay, inside there you have first component and first component here, sine squared cos squared. Alright, so we have sine squared phi cos squared theta plus, and the second component here we have sine phi sin theta. So we have we have take out sine squared phi sin squared theta plus that one a we have take out, so cos squared phi d theta d phi. Okay, then from there just play around with that, do factorization to simplify those terms, so we have a cube sine theta. Here you can factor out sine squared. What left is cos squared theta plus sine squared theta, and then you have cos squared phi d theta d phi. Okay, that gives you 1, that gives you 1, and everything here that gives you 1. So what left is that you just integrate phi from 0 to pi, and theta from 0 to 2 pi. We have a, you can factor out a cube, we have sine phi there, d theta d phi, and then this thing you end up with 4 theta 4 pi a cube, 4a cube theta pi. So that's your answer. Okay, so the main point here is that this formula here, and you need to multiply a find what L is, find what M is. L is just a partial derivative of R with respect to one of the coordinates, one of the parameter, and M also the partial derivative of vector position R with respect to one of the parameter. Now let's see for a cylinder coordinate. So I'll give you another example. I'll give you another example. If you have a flux crosses a cylinder. We know that for a cylinder we have those. We have a cylinder here, that. Okay, so this is your Z, and then you have if you consider any point on the surface, so you have your theta is here, and you need the radius of that cylinder, and yeah, the height, which is Z. Okay, so our representation of XYZ Cartesian coordinate into cylindrical coordinate also I have explained some time ago. So we have S cos theta, Y is a sine theta, and Z you can take as a parameter T, that describe the height of those points. Yeah, and where in this case A is the radius of the sphere, and theta from 0 to 2 pi, because we need full circle here, and our T is the height of the cylinder, let's say from 0, which is base there, and to some height B, say. Okay, so if you consider any point P here on the surface, then those point P, yeah, point P on the surface, on the surface S, which is a cylinder, can be represented as, we consider this as a position vector. Yeah, consider that as a position vector. Then R is given as, in this case, depend on theta and t. So our R is theta and t, function of theta and t. So which is given as, we have our x is a cos theta and y is a sin theta, and our z is t. And hence you can find what L is, or L is differentiate with respect to one of them, d theta. That give you, if you differentiate with respect to theta, that gives you minus a sin theta, a cos theta, and we have 0 here. Yeah, remember that this bracket is symbol for a vector. If you don't use this, you can use ijk, a cos theta I plus a sin theta j plus tk. Try to avoid using a normal bracket, this bracket, because this bracket will represent as a point. Yeah, in the book it's okay because they can make it bold, but when you write, it's difficult to differentiate between those things. Yeah, all right. And then that's your L, and then your M is differentiate R with respect to another parameter. So we have respect to t, so that gives you 0, 0, and 1. So you have 0, 0, and 1. Then your L, your normal, which is L cross M, this is equal to, you can perform this I, J, K, your L is minus a sin theta, your A cos theta, and then 0, you got 0, 0, 1, that give you for I, so A cos theta, for J we have A sin theta, yeah, 0 minus A sin theta, so A sin theta, and then for K you got 0. And for flux, as we have discussed just now, for the spherical coordinate, so therefore flux is given as flux on S f dot n ds. This is integrate over S. We have f dot L cross M, which is n, and this is d theta dt. Okay. Now a particular example for this case, so let's say our f is given as x 0, 0, and the radius of a cylinder, is 3, and height of the cylinder is 15. Yeah, unit you can use centimeter or meter, or centimeter or yeah, you can use any. So find the flux on the surface of a cylinder with those things. Yeah, cylinder with radius of cylinder is 3 and height 15. So for the flux we have SF dot n ds, and we have shown that this is equal to S F dot L cross M d T d theta or d theta dt. This is equal to, this is for the cylinder, right? So our F for the cylinder, our X is that A cos theta, Y is that, Z is that. So but in this case our X is just, our F is just X component of I only. So we have integrate, we have X which is A cos theta, and our A is 3. Yeah, radius is 3, so I put it here 3. And Y is 0, Z is 0, and dot L cross M we have, we already obtained here, A L cross M. We just change A with 3. Yeah, replace A with 3, so we have 3 cos theta, 3 sin theta, and Z component is 0, and dt d theta, dt d theta or d theta dt for t 0 to 15. Yeah, t 0 to 15. For theta full circle we have 0 to 2 pi, 0 to 2 pi. Okay, so that shouldn't be a big problem for you to do this. So we have integrate theta 0 to 2 pi, integrate t from 0 to 15. Here we have 3 by 3, you got 9 cos squared. So we have 9 cos squared theta, the rest 0. So we have dt d theta. Okay, to perform the integral for cos theta, you can use that identity, 1 plus cos 2 theta. All right, and then the rest I think you can do it, which is you got 135 to pi. Okay, now can you do as an exercise? Can you do as an exercise? Use the same function with same radius of a cylinder, same height of the cylinder, but instead we have, let's say this is your cylinder. Oh, should be that. So instead we have that. Now I just want, we have a cylinder with that only, half of the cylinder, and then we have those going up, okay. So we just have this. So height still 15, radius still 3, and our F is let's say just XY. That. Consider this, and as well there's a number 1 and number 2. Consider the sphere a sphere. We have a sphere, no, x, y, z. Okay. That we have a sphere. This should be, and we have those, and we have those. Not good, not good, not good. Let me sketch those things. Okay, that's your sphere. But not whole sphere, but just on the first octant and positive parts. Yeah. Let me write here. First octant of a sphere, of radius. Radius of a sphere, we use the previous example. Where is it? Just consider A. Yeah, that's all. And F is given as x, y, z. F, x, y, z. So means our surface is just on x-axis. Look at on x-axis, this, and y-axis and third axis. So our surface is just this. It's a closed surface, just that, just, and that only. Yeah, that's only. Okay, this is your surface. And that on YZ plane. So YZ plane. So we have a octant of the sphere bounded by a Z plane, YZ plane, XZ plane, and XY plane. Yeah, take the positive part. So try to find the flux for this. We have 2, 1 and 2. Find flux. Okay, so number 1 is that flux. We want to find flux where the surface S is a closed half cylinder here. Okay, with height of the cylinder 15 and radius is 3, where the function, the vector field is given as F equal to that. And the second problem is we have a quarter of a cylinder. I think just 1/8 of the cylinder, and of the sphere, and F is given, vector field is given as that, x, y, z. The radius of the sphere is A, so find the flux crossing that surface. So this is a closed surface again. Okay, so with those more general surface that we have discussed to find the flux, I think I stop here for this video till we meet again in other video. Bye bye for now.